Good morning and welcome to Student Revision Series for Specialist Mathematics presented by Texas Instruments Australia. In today's session, we'll be looking at some graph sketching. My name is Bożena Graham. So what are we going to look at in today's session? We look at the graphs of y equals modulus x, or absolute value of x, with transformation. Then we look what happens if we have some composite functions, modulus of f in x and f in modulus x. How to define a piecewise function on CAS and what the implications for continuity and differentiability with modulus and piecewise functions are. So let's go to the calculator. So recall that y equals absolute value of x is defined as it is x for x greater or equal to 0 and minus x when x is less than 0. How does the graph of modulus x look like? Of course, because that's x for x greater or equal to 0 and negative x, it's our blue line. And I also drew the graph of derivative of modulus x here, and it is positive 1 or negative 1. We can see that there is a sharp point at x equals 0, and the derivative is undefined. It's approaching 1 from the left-hand side and negative 1 from the right and left. Now, if I differentiate modulus x, I get this funny thing, signum x, which we're not quite sure what it is. How can we overcome it? If I use the piecewise function notation, which I will talk a bit more about later, and I differentiate it given in the piecewise function form, I can clearly see that derivative is undefined at x equal to 0. I only know what's that for x greater than 0 and less than 0, not at 0. So just to summarize, derivative is undefined at sharp points, which are called also CAS. And to differentiate a function with modulus, it's better to express it as a piecewise function without modulus to differentiate, to know what is happening. Next, let's have a look at the transformation with our modulus. So if I have a multiplied times modulus x plus b, if a gets bigger and bigger, the graph gets narrower. It's the dilation by factor a from the x-axis. B, of course, will be moving the graph up and down. If I, again, do negative e, then the graph will be reflected in the x-axis, because this is the vertical translation, and a negative is the reflection in the x-axis. If I have f1 in x is modulus of ax plus b, again, I can vary the values of a and b, and interestingly, whether a is positive or negative, it doesn't have that much effect, as we can see. And of course, b will be with a combined with a will be the translation minus b on a, or to the right or to the left, depending on the values. So the conclusion is, as we could see, modulus x minus k is equal to modulus k minus x if k is any real number. This brings us up to our first question, multiple choice question. We are given the modulus x graph, and this graph is transformed by 3 transformations in a given order. We start with the dilation by factor 2 from the x-axis. followed by a translation of 1 unit horizontally to the left, followed by a dilation by factor 1/3 from the y-axis. And we are to determine which one of those 5 options will be the rule of the transformed graph. So let's have a look what the transformations are. But what we'll start with, we'll define our function f in x, and everyone knows how we define functions now. We can get the absolute value from here, but alternatively, you could just type ABS, absolute value. So that's my absolute value of x. The calculator remembers that. Now, a dilation by a factor of 2 from the x-axis, that means that we have 2 multiplied by our f in x, which gives us 2 modulus x. What I will do now, I will store this as f1 in x. So now the calculator remembers that after the first transformation, I have f1 in x. Now I have a translation, 1 unit to the left, which means that I take f1 now, and to the left, that means I need to have plus 1. And this is the rule for the function after 2 transformations. And again, I will store it as my function f2 in x. So now I'm left with the last dilation, and it's the factor 1/3. That means that x is multiplied times 3. So I take f2 in 3x, and I'm given this answer. So this is the rule after the 3 transformations, 2 modulus 3x plus 1, which is option B. I could do a similar thing if I insert a new problem so I don't have those functions predefined, and I again say f is modulus. So if I say absolute value of x, it will work. And now I can perform the same operations. I would say 2 times f1 in x. And now, of course, I can see graphically what happens. Yes, that's a dilation of factor 2 from the x-axis. The graph gets narrower. So now I take my function f2, and I apply the transformation 1 unit to the left, which is my black graph. And then I have the last one. So I take now the function f3 and in 3x, so it gets narrower. So now if you start with this way, and now I go f4, because that was my last equation, I can see I still get the same answer. Going back to the question, of course, if I swap the order of transformation, so let's say if I insert a new problem and go to the calculator and I say, let f in x again be modulus x, so absolute value of x. But what if I apply the dilation first and the translation last? So if I go 2 times f in x, I could do the same 2 at 1, but just show step by step. It's probably easier to follow. And I will say that f1 in x, and now I take f1 in 3x, and now I will store that as f2, and now I find f2 in x minus 1. So clearly I'm getting a different answer. So of course the order of transformation matters. If the question describes the order of transformations, you have to follow this order to obtain the rule. Given the graph, it's a different story. Remember, we dilate and reflect before translate. Next concept we look at are the graph modulus of f in x and f in modulus x. So I have defined my blue graph as x squared e to the power x minus 2. So that's the blue graph. And the red graph is the absolute value in f in x. So we know the modulus is always positive. So whatever was below the graph, below the x-axis, needs to be reflected. So whatever was above, say, this blue part, whatever was below gets reflected. If we now look at h in modulus x, this time my function is x squared e to minus x. That's the blue graph here. So what happens if I now draw h in modulus x? As I can see, whatever was positive, this blue part stays, and the blue part gets reflected in the y-axis. Whatever was to the left of the y-axis totally disappears. The explanation is h in modulus x is an even function, which means that the graph is symmetrical about the y-axis, and h in minus x equals h in x. So that's something to remember when we sketch the graph of h in modulus x. We start with the curve, only look at the positive x values and reflect in the y-axis. So f in modulus x is an even function. The graph of f in modulus x is symmetrical about the y-axis. That brings us to the multiple choice question. The graph of f in x is given in the following diagram, which will be the graph of negative f in modulus x, and we have 5 options. We don't have the equation, and fiddling with trying to match something similar is probably not worth it, so it is better to have a good understanding. So how would we obtain f in modulus x? We take this part and reflect it in the y-axis, so that's like upside down m. And then we have to have a minus, so reflected, which gives us sort of an M shape. So if we look at our options, the only M-shaped reflection is, and even function is part B, so that is the correct answer. Now, if we are to differentiate the function given as the piecewise function, it is good to actually define it as a piecewise function. So we go enter, and now we go to the template, and we have 2 options here. This one is 2 pieces, this one is more than 2 pieces. Because we have 2 pieces, so I enter this one, I can type sign or, and I can go out of 2 minus x, 2 minus x. Now, if you use tab, it jumps between the spaces, and we want x to be greater equal to 1. And again, tab gets us into here, 1 tab x is less than 1. Because it is to be a function, we can include ones only. So now, remembering that we want the derivative of x, and this is our f in x, where do we want it? We want it when x is equal to 3. And of course, we can have that as to some decimal places. If we try to sketch this graph, so because I had this function defined, now if we look at this point, it is a sharp point on the graph. So what happens if I go to analyze graph and I want the y, the x, and this point from memory was 2, it tells me that it is undefined. It also tells me that the function is not continuous here because, as you can see, the graphs do not join. So it's not continuous at 1, and it's clearly undefined at 2 and undefined at 1 as well. So that is the concept of continuity and differentiability of functions. In the course of specialist mathematics, you can be asked to actually differentiate the function which has modulus. Of course, with the CAS, there is no problem. The CAS will handle that. So if I define the function as ln and modulus, just using different ways of entering x minus 1, and now I will try to differentiate it of f in x. It will give me just this answer. Now, if this is an exam 1 and you have some doubts, what you can write this function as a piecewise function as ln x minus 1 for x greater than 1, ln 1 minus x less than 1, and then see, we can't include 1, it's undefined, and see what happens. And when you differentiate, of course, you will see that both derivatives are equal. Let's have a look at another multiple choice question. Consider the function f in x equals x over 1 plus x cubed, and g in x is modulus x. And now we create a new function, h in x, which is the composition f in g in x. And the question is which of the following is true. H in x is an odd function, h dashed in 0 is 0, h1 is in 1 is 2, h in minus x is h in x is concave up for x greater than 0. So, as previously, we'll define this function, two functions and then h in x. So, we have x over 1 plus x cubed. So this is f in x, and I define g in x as absolute value of x, and then I create a composition. H in x is equal to f in g in x. And if I now want to display the rule for h in x, this is the rule for h in x. What I can do, I can draw this graph. So if I get the graph screen and put h in x here, so that's how my graph looks like. Clearly looks like a sharp point at 0, so you could again try to menu analyze graph and dy dx, and if I enter 0, it tells me it's undefined. What I can also do, I can say h in negative x, and I say it's equal to h in x, and the calculator says it's true. So it's true for any value of x. We know it's an even function, so it should be. What happens if I try the even option? So if I say h in negative x is equal to negative h in x, if I want to check it's an odd function which is not, then of course it gives me this particular option. Not saying true, it will be true for x equal 0, but not for anything else, but it's always true for being an even function. If you are asked to sketch the graph like here, y is modulus x cubed minus 1 minus 2 modulus x plus 2, and you are asked to mark axis, intercepts, turning points, and the points of inflection with their coordinates to 2 decimal places where applicable. So let's try to enter this graph as the modulus graph. So if I insert a new problem and go graph, so we have modulus x to the power 3 minus 1, keep out, take away 2 modulus x plus 2. So that's how the graph looks like. You know, the CAS is very powerful, but sometimes it might not handle very complicated relations like that. What I mean, if I try to find the inflection in this form, and I go from here to here, it says none. But I can clearly see that there is an inflection point here. So what I could do instead, I could try to define this function as a piecewise function. How would we do that? We have the point 1 and minus 2. So this is always positive when x is greater than 1. That's always positive when x is greater than minus 2. So I will have 3 intervals, less than minus 2, minus 2 to 1, and 1 to infinity. From 1 to infinity, both pieces are positive. So that's why I just keep the sign. Between minus 2 and 1, the first one needs to be opposite sign. And when x is less equal than 2, both need to change the sign. So what I did here, I actually used this because that is the piecewise number of function pieces, and you can enter more, so I've entered 3 pieces here. Why is it helpful? It is helpful because now if I have a red graph, and I would try to do analyze graph inflection again. Which graph? The red graph. It doesn't want to work for me today. Red graph, I go from here to here. Now I need to do it again, or maybe if I delete this one, and try to do it again, analyze graph and inflection. It doesn't want to work for me today. It did work the other way. It will pick up the inflection point on this graph. So what we'll try to do, we'll try to copy that and we'll do new problem. Just to sketch this graph only, and I will copy this, but just without H, and let's see whether it will work. So now I have this graph as a piecewise function. I might hide that because it's in place. And now if I try to do inflection, it will pick up the inflection point as 0, minus 3. I can find the zeros as well. So I have 1, 0 here. And then menu analyze graph 0. I can find the other one. It is to 2 decimal places. If you need to change the setting, we have the settings here, and you could play with the float. I could change it to float 4, and then it displays more. So there is the way of changing settings being in the graph screen. And we also have the minimum point, analyze graph, the minimum when it's not quite a stationary point, but that's the lowest point on the graph. So trying to define this function given, let's say in the exam, as the piecewise function with 3 pieces allows you to manipulate things on the graph better. Later, if you are to find the areas or use it for arc length or use questions of this type in kinematics problems, then that will be helpful. So we've learned how to do the transformations with modulus graphs, how to change the piecewise functions to how to change the modulus functions to piecewise functions, how to use CAS efficiently for various options. So that's all we're learning in this session. There is students' handout, which will have some more problems for you to practice on the concepts we were discussing in this session. Thank you.